So here's a definition. Given any two functions f of x and g of x, the composition of f of x and g of x is denoted as f composed with g at x. That's how we actually write that f is being composed with g. Let me start from the beginning. And given any two functions f of x and g of x, the composition of f of x and g of x is denoted as f composed with g at x. That's how you write it. And is defined as, now here it is, this is what it means. F composed with g at x is f of g of x. All right, you may want to highlight this in your notes. This is really important. This is how you are going to compose two functions. But I really want you to focus on this side of the equal sign, right? This is really what it means. All right, here we go. This is example number 6. This is be the first example that we look at for function composition. Example 6, let f of x be equal to 3x minus 7 and g of x be equal to x squared plus 2x. Okay, I want to be very clear. These two functions are given to you, okay? These are given. What they want you to find is the following. Find the following, okay? F composed with g at -4. Now, there's a few things that I want to say about this. First of all, this f composed with g is a function. It's a composite function. F composed with g is a composite function. And they're basically asking you to find the value of that composite function when you plug in -4. So f composed with g at -4 is, and that's what you have to figure out. They gave you the input of -4, you find the output, or as we like to call it, the function value. Now, I'm going to apply the definition right above here that I wrote, and I actually underlined it in red for you. So reading this definition above, I highlighted it I put a big old blue box around it. It reads as follows. F composed with g at x is equal to f of g of x. Therefore, reading our problem, f composed with g at -4 will be equal to f of g of -4. This is me applying the definition of the composite function. All right, I'm going to move this screen up a little bit so that I have room to figure this out. Okay, that should be good. All right, here we go. So I want to explain this a little bit before I actually do it. They're asking you to actually plug -4 into g first. And then whatever you get as a result, plug that result into f. I'll say that one more time. Plug -4 into g first, and then whatever you get as a result, plug that into function f. All right, here we go. So we have f of, now we need to plug -4 into g, okay? Now g is the, well, I guess I moved the screen up just a little too far. There. G is the quadratic function x squared plus 2x. So when I plug -4 into it, it's -4 squared plus 2 times -4. All right? This is me plugging -4 into g. All right, let me close this off here. All right, cool. So I need to figure out what that is. So this is equal to f of, again, I'm not ready to do anything with f yet. I got to figure out what g at -4 is. -4 squared is 16. 2 times -4 is -8. So then we have now f of 16 minus 8, which is 8. So you can see now that what we're going to be plugging into function f is the value 8. So here we go. Function f is up here, 3x minus 7, so it'll be 3, excuse me, I think I want to write in red. 3 times 8 minus 7. All right. Again, let me move this up just a little bit here. So what we have now is, of course, 3 times 8 is 24 minus 7. So then our final answer here is 17. This is the function value, guys. So f composed with g at -4 is 17. You plug -4 into that composite function and you'll get 17 out. All right, cool. I hope that was clear for you. All right, so let me give you another example here. All right, this is still example 6 though, okay? Let's call it example 6. What I mean to say is f of x is still given as 3x, that's an equal sign right there. Let me clean that up. F of x is still 3x minus 7. And g of x is still the same. G of x is x squared plus 2x. Okay, so that hasn't changed. Again, these are your two given functions. All right, so this is the next thing we want you to find, okay? So the next thing that you'll find is, all right, here we go. Let's find f composed with g at 1. So f composed with g at 1. Okay, guys, this next example here is pretty much exactly the same as the previous example. The only difference is that you're dealing with the number 1 here instead of, what did we have earlier? -4. So why don't you pause the video right here and then try this out on your own. All right, so let's see how you did. I'm going to show you the whole solution. All right, here it is. So f composed with g at 1 is, by definition, f of g of 1. So we plug 1 into g first. So that'll be 1 squared plus 2 times 1, which turns out to be 3. And then I plug 3 into f, which would be 3 times 3 minus 7, 9 minus 7, which is 2. I hope you did well on that one. Let me give you a couple more to consider. All right, let me move this screen up. Oops, sorry. Let me move this whole thing up. There we go. All righty. Okay, the same two given functions, all right, everybody? All right, f is still 3x minus 7. G of x is still x squared plus 2x. The last two examples, I'm going to write them both down at the same time here. So find each of these. G composed with f at 2. Now notice here, we changed the order of the composition. Instead of f composed with g, it's g composed with f. And then the next one, when you're done with that one, maybe you can try this one. F composed with itself, f composed with f at +4. So these are two more examples to wrap this up. So why don't you pause the video and try both of these right now. All right, cool. So let's see how you did on this first one. I'm going to actually work it out live for you right now. So then this is, by definition, g of f of 2. Okay, I'm doing this first example first. G composed with f at 2. All right, cool. So then this is equal to, now, the first thing we want to do is plug 2 into f. Plug 2 into f. So then it'll be 3 times 2 minus 7. Figure out what that is, which we can see is going to be 3 times 2 is 6, so 6 minus 7 is -1. So then we want to plug that value of -1 into g. So let's do it. G says, it's up here, x squared plus 2x, right? So then it'll be -1 squared plus 2 times -1. All right, so -1 squared is +1. 2 times -1 is -2. So it'll be 1 minus 2 to give us our final answer of -1 is the function value. G composed with f at 2 is -1. I hope you did pretty well on that one. Now it's time to do f composed with f at 4. Again, if you haven't had time to do that one yet, why don't you pause the video and give it a shot. All right, cool. Here's the solution. Check it out. See if you did pretty well. It's f composed with f at 4, which is f of 4. So you need to plug 4 into f. So that's 3 times 4 minus 7, 12 minus 7, which is 5. Now it's time to plug 5 into f. So 3 times 5 minus 7, 15 minus 7, which is 8. Good job, guys. All right, let's look at a brand new example. We are moving to example 7. All right, guys, we're at example 7 here. Let f of x equal 3x minus 7. G of x is x squared plus 2x. The same two functions we've been working with. This time around, notice the instructions say find each function. Example 7 is different from example 6 that we were working on a few minutes ago. Example 6, you were finding function values. That is to say, they gave you an input and you found the output. They gave you a real number to plug in, and you found the real number output. This time around, they've given you the two functions, f and g, but you're finding a function. Not a function value, but a function. All right, so the first function they want you to find is f composed with g at x. All right? This is the first function they want you to find. All right, let's work this out together, all right? By definition, guys, we know that this is the same as f of g of x, right? I know that, we know that by definition. Now, the way this is going to play out is f of, now watch this, g of x is the same thing as, you can see up here, I'll highlight it for you to kind of draw your attention. G of x is the same thing as x squared plus 2x. So I'm going to replace g of x over here in my problem with what it's equal to. X squared plus 2x. That's what g of x is. So this notation now that we have is asking us to substitute x squared plus 2x into function f as your input. Now, when you look at function f, I'm going to draw your attention up here. This is your input value right there. So you are replacing that input variable, x, with the expression x squared plus 2x. So you know how your function f reads 3 times x minus 7? Well, now it'll be 3 times x squared plus 2x minus 7. In other words, it'll look like this. 3 times x squared plus 2x, and then don't forget minus 7. All right? So then this is going to give you, we have to distribute that 3. I'll show that. Distribute the 3 to both of those, right? So then you get 3x squared plus 6x, and then minus 7. Guys, this is a function. This is a function. 3x squared plus 6x minus 7. You and I already know that this function is quadratic, isn't it? It's quadratic. It's degree 2. Now watch this. Because it's quadratic, we can determine its domain. Because it's actually, let's actually be a little more broad than that. Because it's a polynomial function, we can determine its domain. You and I studied polynomial functions a while ago, and any real number input will give you a real number output. This particular graph will be a parabola opening upwards, and we know parabolas go forever to the left and forever to the right. So we've studied how the domain of all of our quadratic functions is all real numbers. So because I know what kind of function this is, I know what its domain is. So we found the function, and we also were able to say what the domain is. All right, cool. Let us look at another example. All right, the next function they want us to find is g composed with f at x. Notice that they're just turning around reversing the order of composition. All right, you want to give this one a shot? Go ahead and pause the video and try this one. All right, we're back. And so by definition, this will be g of f of x by definition, right? All right, so here we go. So then this will be g of, now what you're going to see me do is replace f of x with what it's equal to. Now f of x is the same thing as 3x minus 7. All right, cool. So this notation says substitute 3x minus 7 into function g and simplify. Now, I just want to draw your attention to something. Function g has two input variables, one right here, I'm underlining it, and right there. So you are replacing both of those input variables with the expression 3x minus 7. So the way that'll look is 3x minus 7 quantity squared plus 2 times 3x minus 7. So you can see we have some simplifying to do. All right. So 3x minus 7 quantity squared, we know that that means 3x minus 7 times 3x minus 7. And I think I need to move this over a little bit that way. All right, cool. So let us as well, while we're here, distribute this 2. Okay, so then this is plus 6x minus 14. All right, very good. Over here, we're going to, a lot of you know the acronym FOIL, which just means you need to distribute. So we're going to distribute 3x to 3x and negative 7. So 3x times 3x is 9x squared. 3x times negative 7 is minus 21x. And we have to continue our distributing, so negative 7 times 3x, and then negative 7 times negative 7. Negative 7 times 3x is negative 21x again, and then negative 7 times negative 7 is positive 49. Let's not forget to bring down the 6x minus 14, all right? Very good. So what we have here, let's see. We can combine these two like terms right there. And also with this one as well. So negative 21x, negative 21x, and then a positive 6x. At the same time, we can combine these constant terms, positive 49 and negative 14. When you combine all of these like terms, you get 9x squared. What is this? Negative 42 and then plus 6. So that'll be minus 36x. And then 49 minus 14 would be positive 35. Okay, positive 35. All right, cool. This is our final answer, which is a function, right, everybody? This is our function. Okay, what kind of function is this? Quadratic. Very good. So because it's quadratic, you and I know what its domain is. What is it? All real numbers, right? Awesome. Okay, cool. Let us find one more function. All right, here is f and g again, and this time around they want you to find this composite function, f composed with itself, f composed with f at x. All right, everybody, like usual, I would like you to pause the video and try this out on your own. All right, how did you do? F composed with f at x means f of x, which is f of, now replacing f of x with 3x minus 7, gives you f of 3x minus 7. Then you take 3x minus 7 and plug that expression into f. So it's 3 times 3x minus 7 and then minus 7. You see me distributing the 3, which gives me 9x minus 21. Combining like terms gives me my final answer of 9x minus 28. All right, cool. There's the function. Now, what kind of function is our answer? What kind of function is 9x minus 28? If you said linear, you are correct. This is an mx plus b form. So, because it's a linear function, what's its domain? Well, you and I know that all linear functions have a domain of all real numbers. How do you know that again? Well, this line, the graph would be a line, and we know that our linear functions, the graph of them would be a line going indefinitely in both directions, to the left forever and to the right forever. So the domain is all real numbers. I could have also said that the domain is all real numbers because 9x minus 28 is a linear is a polynomial function of degree 1. All right, very good, guys. All right, here we go to example 8. Okay, so this is going to be your brand new given function, all right? So let p of x be 2x plus 5. Notice that this is a linear function. And let q of x be the square root of x minus 3. All right? What they're going to want us to find is some functions, some composite functions, and their domain. All right, find each of the following composite functions and their domain, all right? So the first composite function they're asking us to find is p composed with q at x. All right, very good, guys. Let's go for it, all right? Let me do this problem with you. By definition, p composed with q at x is equal to p of q of x, right? Probably used to that by now. All right, so here we go. So p of, now q of x is the square root function, the square root of x minus 3. Okay? Alrighty, so then what this notation really means here is that we want to go to function p and plug in the expression, the square root of x minus 3, into function p for the input variable. So here, if I can point your attention to function p up here at the top of the screen, here's your input variable right there. Replace that variable x with this radical expression, the square root of x minus 3. All right, so then that'll look like this. 2 times the square root of x minus 3, and then plus 5. Now, this is as far as you can go, to be honest. I mean, this is the function that we found. You cannot distribute the 2 inside the radical. You can never do that. You cannot add the 2 and the 5 together because they are not like terms. 5 is a constant term, and 2 is being multiplied by this radical. So really, fight any temptation to kind of simplify this. You are done. Now, let's talk about its domain, shall we? Now, the only thing... I really want you to look at function p, the original function p. It's a linear function, so the domain is all real numbers. Q, however, is a square root function, so we have to be careful about what we plug in for x here. So let me move the screen up a little bit here. About right there would be good. So as far as its domain is concerned, when you look at this square root expression, the square root of x minus 3, let me rewrite it right here, the square root of x minus 3. We want to make sure that the radicand, now the radicand is just the expression that's underneath the radical. We want to make sure that that radicand remains positive. Why? Well, if the radicand becomes negative, then you're going to have the square root of a negative number, which would give you imaginary solutions, right? So in order to stay in the real number plane and to get real number outputs, we want to make sure that x minus 3, that expression, is greater than or equal to 0, all right? And this is to avoid imaginary solutions, all right? Let me add that to our notes for us. All right, I added this note for us. To avoid imaginary solutions, the radicand, which again, the radicand is just the expression underneath the square root, must be greater than or equal to 0. So that's why you see me setting it greater than or equal to 0 here. And now I'm just going to solve for x by adding 3 to both sides of this inequality. So add 3 there, add 3 there, and then you get this expression that x must be greater than or equal to 3. X must be greater than or equal to 3. So the domain for this function that you and I found can be any real number as long as it's greater than or equal to 3. Any real number as long as it's greater than or equal to 3. Okay, so that means bracket at 3. Again, a bracket at 3 means that we are including 3 in the domain. If you would have put a parenthesis at 3, that would be excluding 3. But we can actually include 3. And then you want to plug in any number greater than or equal to 3. So that means we're going to go toward the right on the x-axis all the way to positive infinity. Remember that you always put a parenthesis on positive infinity or negative infinity because they are not real numbers, so you cannot contain them. So here is your domain for this function, all right? So you want to do something similar to this whenever you have a square root involved in your function. Cool. All right, guys, let's do another example. This is actually still example 8 with p of x equal to 2x plus 5, linear function whose domain is all real numbers. You got q of x here, the square root of x minus 3, whose domain is any real number greater than or equal to 3. All right, we're going to find a brand new function, a composite function, and this time around it'll be q composed with p at x. Q composed with p at x. All right, very good. I don't know, you may want to pause this video and try this out on your own using the previous example as kind of like a guide. All right, so go ahead and pause the video and give this a shot. All right, we're back, and let's see how you did. So Q composed with P at X, by definition, is Q of P of X. All right, very good. That's the first thing we should write. All right, so this is equal to, what we want to do here is, let's see, we got Q of, now P of X is the linear function 2x plus 5, all right? So really, this notation is suggesting for us to input 2x plus 5 into function q. Now, let me see if I can highlight. For function q, your input variable is right there, right, underneath the square root. So we're replacing that input variable that I've highlighted with the expression 2x plus 5, okay? So it'll look like this. The square root of 2x plus 5, and let's not forget, minus 3, okay? All right, so what we have now is the square root of, and combine like terms here, 5 minus 3 is positive 2. So here is our function. This is our function. It's a square root function, a square root function. The square root of 2x plus 2. All right, good job, you guys. Now, what I would like for you to consider is, what is the domain of this function that we just found? All right, cool. Let's talk about it. Now, the domain of this square root function, in order to have real number outputs, we have to be careful about what we plug in for x. Now, the same kind of conversation that we had a few minutes ago, to avoid imaginary solutions, we have to make sure that the radicand, the expression underneath the radical, must be greater than or equal to 0, right? So now what you see me doing is solving for x. We're solving for x because the question is, what is the domain? And the domain, by definition, is a set of your x values. So when I subtract 2 from both sides, I get 2x is greater than or equal to negative 2. What I want to do next is divide both sides by 2, like this. And what I get here as a result is I get, now if I could just kind of come up here, I get x is greater than or equal to negative 1. All right, very good. So then this is your domain. Of course, this is not an interval notation, but I'll write that out for us right now. So interval notation, again, we want to, in words, maybe this will be helpful. In words, we're saying that the domain for this composite function is any real number as long as it's greater than or equal to negative 1. Greater than or equal to negative 1. So in interval notation, it'll be from negative 1, inclusive, all the way to positive infinity. Good job, you guys. All right, you guys, we got some brand new functions on the board here. Well, we will in just a second. Example 9, let g of x be 3 over, that's number 3, make that a little better for you, 3 over x minus 2. Do you know what kind of function that is? Want to take a shot at it? What kind of function is g? If you said a rational function, you are correct. We dealt with rational functions in an earlier chapter. All right, and then another function is going to be h of x, and that'll be equal to the square root of x plus 4. What kind of function is h? You could either say it's a radical function, or you can be more specific and say it's a square root function, and you'd be correct. All right, very good. So these, again, these two functions, g and h, are given to you, all right? These are definitely given to you. All right, and what they're going to ask you to do is to find a function, all right? So these are the instructions. Find the function, find the composite function, and its domain, all right? So find the following composite function and its domain, all right? This is what they want you to find. They want you to find g composed with h. G composed with h at x. This one's going to be, I think it's going to be a really interesting example here. I think it's going to be a lot of fun, okay? All right, here we go. By definition, g composed with h at x is equal to g of h of x. Cool? That's by definition. Now, here we go. This is equal to g of, now I'll replace h of x with the expression that defines it. So h of x is defined as the square root of x plus 4. All right? Cool. So this notation, again, means that we need to plug x plus 4 into function g. Now, I'm going to highlight this for us. Function g is over here, and the input variable is right there. So we want to replace that input variable x with this expression, the square root of x plus 4. All right? So let's see if I can show that to you clearly here. So it'll be 3 over, now replacing x with the square root of x plus 4. And then don't forget, you got a minus 2 down there. All right? Cool. Hey guys, we're done. This is the function. I know it's not, maybe you would say that's not pretty. Well, you know, nobody ever guaranteed that it'd be pretty, but it is a function nevertheless. All right, cool. So what we want to consider now is, what is the domain for this function? What is the domain for this function? All right, so there's a few things to consider. First of all, you see this radical expression in the denominator right here. I'm going to highlight it. That radical expression in the denominator. We had a conversation about this before, and that is the square root of x plus 4. To avoid imaginary solutions, right? To avoid imaginary solutions, x plus 4, do you remember? Has to be what? Greater than or equal to 0, right? To avoid imaginary solutions. We talked about that before. All right? So, you know what might make it a little more clear here is if this white arrow were something like this. That way you can see, like, where is that coming from? All right, cool. So in order to avoid imaginary solutions, x plus 4, which is the radicand, the expression underneath the radical, must be greater than or equal to 0. Now, when you subtract 4 from both sides here, you get that x must be greater than or equal to -4. All right, so I want you to put that aside for the time being. So I'll just kind of highlight that. Now, in addition to that, there is something else we have to consider as well. All right, there's something else that we have to consider as well. Let me see if I can do a little bit of erasing here. Just give me a second here. I want to kind of erase this arrow. All right, so in addition to that, we must also say that this entire denominator, the square root of x plus 4 minus 2, this entire denominator must not be what? Can you try to answer that question? The entire denominator, for any fraction, the entire denominator must not be equal to what? To 0. Very good. Because if the denominator turns out to be 0, then the whole function's undefined, right? And so we want to figure out what makes this denominator become 0, all right? And whatever real number makes the denominator 0, we have to exclude that number from the domain. All right, so let's do it. Let's do this work together. All right, so in order to figure out what x value makes the denominator 0, we have to solve this statement here for 0. So, for x, excuse me. So what the first thing you're going to see me do is add 2 to both sides. Let's do that. Okay, this will give me the square root of x plus 4 must not be equal to positive 2, right? It must not be equal to positive 2. All right, move this up a little bit. Let's continue working. What do you want to do at this point to solve for x? If you thought about squaring both sides, good job. So you're going to see me square both sides. So you're going to see me square this left-hand side here. You're going to see me square the right-hand side there. Squaring will undo the square root, right? They're kind of like inverse operations or opposite operations, so that all you're left with on the left-hand side is just x plus 4. Must not be equal to 2 squared, which is 4. Cool. Let's continue working, guys. Let's solve for x. We're about done. Subtract 4 from both sides. When we say solve for x, don't forget we mean isolate x, right? Get x by itself. So then x must not be equal to 4 minus 4, which is 0. All right? Let me kind of highlight this for us. So look at these restrictions on your x variable. The very first one that we found is x has to be greater than or equal to negative 4. And the second restriction is x cannot be 0. Again, those two combined, x can only be greater than or equal to negative 4, and it must not be 0. Now, to maybe help us figure out what the domain is, would you allow me to draw a picture for you? Now, you don't have to draw a picture, but I just think for the visual learners, it would be helpful, hopefully. So when you look at your x-axis here, right? So I'm going to say this is negative 4. I'm going to say this is 0 right here. We're saying that x can be or must be greater than or equal to negative 4. So it's like I'm going to put a closed-in circle here or a bracket. The closed-in circle, that bold circle there means that negative 4 is included. So you're going from negative 4 to the right, correct? But when you get to 0, you have to exclude 0. So like maybe put like an open circle at 0 and then keep going, right? Forever. So this is your domain. Any number greater than or equal to negative 4, but you have to exclude 0. So let's see if you and I can write this in interval notation. All right? So I'm going to move the screen up just a little bit. There we go. So your final answer, as far as the domain is concerned, will be, let's read our graph, this x-axis from left to right, a bracket at negative 4, bracket meaning negative 4 is included. It's equivalent to that closed-in circle, comma, you got to stop at 0, exclude it, which means put a parenthesis, which is equivalent to that open circle, union from 0 to positive infinity. To positive infinity. All right, so then this is your domain. kind of like box that for us. This is the domain for that composite function that you and I found. All right, the domain. Okay. Any real number as long as it's greater than or equal to -4 and as long as it's not 0. Great job, guys.